All right. So today, just briefly, we will do a lecture. We will recap whatever we have done so far, and in the next lecture, we will be starting Turing machine. Right. So last time we have stopped uh, with this quiz, which many of us have not made correct. Right. So let's look into this. So first question was how many variables are there in G? Right? So non-terminals, terminals, they are two different things, right? So when you say variable, just a minute, I think this needs some, yeah, so the variables are this denoted in capital letter usually, right? So all those are X, T, S, all these are variables, but the terminals are A and B. Right? The terminals are symbols. They are a small sorry small a and small b. So this is small a small b. They are not uh, variable. Right? So they are constants. Okay. Right. So what is the right answer? So you have R is there, X is there, S is there, T is there. Right? So four. Out of 9 rules in G, so this is G, how many are not in CNF? How many are not valued in CNF? Kind of like. So, first of all, what are these 9 rules? This is rule 1, this is 2, this is 3, this is 4, 5, 6, 7, 8, and 9. So, out of these 9 rules, how many are not in CNF? Is the first one is in CNF? First one, you guys can say yes, no, no, right? First one is not CNF. Second one, no. Second also no. First is this is no. Second is also no. Why no? Because you do not have. So what is CNF, right? So CNF is nothing but A implies BC and A implies A. Only these two are allowed, right? And additionally, you have this is also allowed. So this one, so here S is a start symbol. Allowed. 5 is not allowed. 6 is also not allowed. 7 is also not allowed. Right? 8 is fine. 9 is also fine. So 7 are not in CNF, right? No, so 7 are not in CNF. All right. Okay. What describes language G? Language corresponding to this grammar. Many people have made a mistake that they are calling it a palindrome, but it is not a palindrome. If you look into this language, R implies XRX. By looking first production rule, it looks like it is palindrome, right? So what it is saying is R X R X, right? But the X can be anything. It can be A, it can be B, right? This can be A, this can be B, right? Or even if they are A, let's say, even if they are A. Let's try to create a, let's try to come up with a palindrome using these production rules. Will we able to do that? We will not. So next is R is, let's say, R can be S, right? R can be S. S is ATB. ATB or BTA? ATB. This itself says that this is not never be palindrome because okay, it starts with A, it ends with A, but it starts with, but the second character is A. Second character from the left is A, but second character from the right is B, right? And even if you apply BTA, the similar thing will happen. That means that this is not palindrome. So this is actually all the things which are not palindrome. So it's like, so the language it will make is a, like I can say this is the palindrome complement. Palindrome complement. Everything which is not palindrome. Is that clear? Because many of you made a mistake here. Okay. And there was one more question. What was that? That also people made a mistake is like T generates T. Is true or false? This is false because there is no such rule, right? So T is its identity. This is T generates T means there should be some identity type rule in the production rules, but there is no such rule. T will, whenever there is T, T will be replaced with either XTX or X or epsilon, but T will never generate T. Okay, so this is false. So these were few questions which were asked in the last quiz or last CPQ. So now let's quickly look into NPDA and PDA. Right? So we said that non-deterministic PDA is nothing but PDA. So when they are same, right? So whenever we say PDA means non-deterministic PDA itself. PDA by default it means non-deterministic PDA. But what is then DPDA? DPDA means deterministic PDA. So there is some difference. The difference is the transition. Only difference is in the transition, right? So in transition there is a difference. Okay, we'll come to that question, but let me finish this part, so then we'll take a question. So we are talking PDA and NPDA, right? So the major difference is in PDA, if you remember, the delta is between set of states, right? Sigma, which is sigma epsilon means the input alphabet, right? And lambda epsilon means, what is this? Anyone? In the PDA. So power set of Q what is this? Stake alphabet, correct. All right. So this is power set of this, right? So this is a major difference. In NPDA, let's write it here itself. So NPDA, there is a difference. Sorry, this is same as NPDA, right? So this is NPDA. These are same, but this is deterministic PDA. DPDA. DPDA, the only difference will be here. So then Q not these are allowed. This is allowed, but this will be not power set. Rather, it will be Q into this union Y. So this is called deterministic PDA, and the thing is, these two things are not equivalent. NPDA is not equivalent to DPDA. In fact, NPDA is slightly more powerful than PDA, DPDA. Okay, so but we will not discuss too much about this. What is inside the DPDA, and that's not beyond this course. So, but only thing which we should know that there is a difference, and PDA and NPDA are same. And in terms of language, if you remember, the regular language is the simplest one, right? And then there is this context-free language, CFL. And the CFL is actually recognized by PDA or NPDA. In between this CFL, there is another language which is called deterministic CFL, which is called deterministic CFL, right? So deterministic CFL, and in this deterministic CFL is recognized by DPDA. And obviously, you know, regular language is finite automata, or equivalent is NFA. DFA and NFA are equivalent, so regular language is recognized by them. There is something called deterministic CFL, DPDA, and there is something called PDA or NPDA, right? So these are same. PDA and NPDA are same. This is the hierarchy we are leading to. So far we have seen context-free language, right? So beyond that is what we will discuss in the next class. But this is beyond that is called context sensitive language and type 1, type 0 languages. We'll see all those. So let's take one example which we have already done, but we just to repeat it so that you understand the difference between DPDA and NPDA. And this example is WWR. Right. So if you remember, we have already done this when we were doing PDA. So this is a language L, right? WWR. WR means the reverse of W. So that W belongs to 0, 1 star. All right. So this language, we can, for this language, we can definitely design, PDA, right? PDA and NPDA are same, but we cannot design DPDA. Deterministic PDA will not work for this. For this, deterministic PDA will not work, but non-deterministic PDA will work. So if you remember, this is what we have drawn it already. So you have a state Q1, and without doing anything, you can go to the empty state, right? So you can go to the empty state. Yeah, without hitting, and just push the dollar, right? And if there is 0, you will push it. If 1, you will push 1, right? And if there is 0, we will erase 0. If there is 1, we will erase 1. And then we will go to, if there is nothing left, right? And if there is dollar, we will go to this. Final state, right? Q2, Q3. So this is what we have already seen. This is for push down automation for WWR. Right? What we are doing is pushing a stack, and whenever there is zero, we will push zero. Whenever there is one, we will push one. But this whenever we know that there is uh, change, right? So whenever we finish W, after that we will jump to Q3, right? And in Q3 we will be popping. So this is kind of a pushing. This is pop. So push all the zeros or ones, whatever is coming, and then you start popping. But who will tell this? You might ask a question. Who will tell me that when to from when I start pushing when should I stop pushing and start popping, right? When should I stop pushing and start popping? Who will tell you? So this is where the non-determinism is there, right? So non-deterministic, we have discussed that this non-determinism is like a god. So that is the thing. Like, so you don't really know, but where it actually in the deterministic way, you will never know where the WR will start, right? How do you know? You will never know. But in the non-deterministic way, you can know this, and this is what is non-deterministic. So this language cannot be recognized by DPDA, deterministic PDA, but non-deterministic PDA is doing this. Any doubt on this? Okay. So the next thing is, if I ask you another language, if I give you and ask, let's say L is WCWR, right? C is another symbol. So where this W is, let's say 01 star, and of course your this is 01C. Okay. Can this language be recognized by DPDA, deterministic PDA? Deterministic. Can deterministic? Yes. Right? Because why? Yes. Because you know where the center is. So you will. So you know the answer for this question. You know answer for this question. When should I stop pushing and start popping? When should you stop? When should you do this? What is the answer for this question? When should I stop pushing? So your answer is when you reach to C, you should stop pushing, right? And this is what is the non-deterministic solution for this. So your non-deterministic solution will be, deterministic solution. So let's call it Q1. Without reading anything, I'll push dollar, all right? And then what I can do here, I can push. Whenever I read 0, I will push 0. Whenever I read 0, I will push 0. Whenever I read 1, I will push 1. And whenever I read C, right, whenever I read C, I will not push anything, right? So what I will do? Nothing. Not going to do anything. And then whenever you read 0, you will erase 0. Whenever you read 1, you will erase 1. And then whenever you yeah, so whenever you read nothing, right? Dollar, erase, and Q final, right? So here you can see that though it is not a deterministic PDA, we still have epsilon, right? So you can ask why is that? In deterministic finite automation, we do not have that, the epsilon transition. But here epsilons are there because you are still doing some push-pop operations without or you're not doing anything on the stack. And if you remember the definition also, right? So if you remember the definition, uh, the DPDA also have epsilon symbol. So epsilon symbols or the epsilon transitions are allowed. Only thing is it is deterministic in nature. It is not like going. It is not like two transitions possible, right? So that's the only thing. So here also, if you look into this example, reading by not reading anything, you are pushing dollar. But this is a deterministic state, right? It's not. This is not a non-deterministic. Okay, so we will quickly discuss few more things which by someone who has asked about question number one, exercise number, or example number, problem number 1.53. Right? So this is in problem 1.53 from the textbook. Let's do this because I don't want to start, let's say, the Turing machine today in the between. We have less time. We can do is we can start Turing machine in the tomorrow lecture. But let's do this 1.53, which is one interesting question. So this is a question on finite automation. No? This is not DFA question. Well, let's do it. Okay, so the question is, you have sigma given, that is 0, 1, and right, and you have D given, which is a language, and this language is W, such that W contains an equal number of occurrences of occurrences of these substrings substrings 0, 1 and 1, 0. Okay, and this was given, and the question was so that D is regular, so that D is regular. To show something regular, right? To show something regular, what do you need to do? Anyone? To show some language is regular, what do you do? Not really. Pumping lemma is not a right way, perhaps, because pumping lemma is usually we do for showing non-regular. Like, of course, you can do that also. Nothing, no harm. If you can show, that is fine. But the pumping lemma use if there is you have to show something non-regular. You can show that using contradiction. You can prove that using pumping lemma. But the best way is to show something regular. You design a finite automation for that. If you design a finite, you can design the finite automation. Then obviously that language is regular, right? So we will try to design a finite automation for this particular language. Though this language looks like very similar to equal number of zeros and ones, no? That is not, so there is another language, let's call it D1. W W contains equal number of zeros and ones. Is D1 regular? Is D1 regular? More answer. Is D1 regular? No. Right? You may not able to design such language which contains equal number of zeros and ones, right? So one may try something like this just as a thought. This will not work. Like maybe whenever I read zero and then I read one. Okay? But is this a correct answer? No. Right? Because why it is not so? This is reading 1011, 2021, and so on. It is doing, but what is the transition for here? What is the one transition for here? What is the zero transition for here? That is not defined, right? So that we need to define. So you can actually not do this. So you may not able to find finite automation for second language. But the first language, which is also looks very similar to the second language, right? So D and D1, they look very similar. How come D is regular and D1 is not? Right? So we'll see. So in D1 now, let's try to understand D1 a little bit more. So let's first say what is there in this language. So if I ask, let's say 101, is this in this language? Yes, no. Is this D101 belongs to D? Yes. Right? Why? Because there is 110 and then there is 101. So 110, 101. Okay. So this is yes. What about 11101? This is also yes. No. There are some no. For the first, there is no or second. First, second, third. First is yes, right? Because there is 110 and 101. Similarly, second also there is 110 and there is one, both are indeed yes. But what happens? So there can be many such examples, right? So you can start with 010. This is also valid. But something like let's say 1110 is not. Is not because there is 110 but not. So it essentially what is happening is it is actually using the fact that 10, whenever there is 10, next it is looking for 1. That's all, right? So whenever you read 10 and you reach at some state, in that state you just have to look for 1. And so you are actually not counting this, so let me say like this. So you don't have to maintain a counter which for a longer time, right? If I say like that, that is good. So you don't have to maintain a counter for a longer time. Why is that? So let me say that. You do not have to maintain a counter for long. What do you mean by what do you mean by this? I mean by this that when you are reading a string, only thing you have to maintain the counter is like whenever you read 10, next you should be looking for 1, right? So the counter is not maintained for long. But in the other example, if you remember, equal number of zeros and ones, the counter has to be maintained for long, right? So I can have an example like 0, 0, 0, 0, 1, 0, 0, 0, 1, and then so 1, 2, 3, 4, 5, 6, 7, 7, and then 2, 3, 4, 5, 6, 7. This language, if I have to count equal number of zeros and ones, I have to really maintain this counter. No, I have to remember throughout this. But in this example, what you are doing just now, D, this D, you do not have to really remember, right? You don't have to memorize that for a long. Only thing you need to do is whenever you have 0, 1, you should be looking for next, like 0. That's all. So we'll draw this. Let's maybe simply draw it. Very simple DFA. The first thing is, so what are the base cases? Like it should obviously empty is trivially true, right? So empty is in D, 0 also is in D, 1 is also in the D, and then something more, right? These are all in D. So since empty is in D, my first state will be also final state. Since 0 is also in D, right? So 0 and 1. Now when I read 0, right? When I read 0, when I read 0, even if I read many zeros, doesn't really make any difference, right? However times I read 0, it does not make any difference. So I'm looking into the top branch, which is 0, where you read 0. Now, even if you read 0,000 times, what difference it makes? It does not make any difference. Only difference we need to make is when there is 1, right? When there is 1, we need to change the state, right? So what do you mean by that? That now you are in the stage 0, 1 you have read. Now you should be looking for 0 to reach the final state. Whenever there is 0, you will go to the final state. Right? Whenever there is 0, you will go to the final state. But if you read 1, it doesn't really make any difference. This will be 1. Right? And in the similar way, when you read 1, right? When you read 1 and you read more ones, doesn't really make any difference. You will be here only. But when you read 0, you have to be like, what you have to go to the alert state, right? Why that is true? Because once you read 1, 0, you should be alert so that if 1 comes, I should reach to the final state. So whenever there is this 0, so 1, 0, I will go to the alert state. So let's call this guy's alert state. Just to you are alert now. And whenever you again read 1, right? Whenever you again read 1, you will go to the final state. If you read more zeros, no problem. Right? So this way we have designed this DFA for D. Any question on this design? This is the DFA for D. DFA for D. Okay, and therefore D is regular, and this is the like this. Although by looking into the first glance, it doesn't look like a regular language because it looks very similar to 0 equal number of zeros and ones. But if you analyze, since you do not have to maintain the counter for long, right? You can actually afford to do this because yeah. So you have this luxury of forgetting things, right? So even if what I'm meaning, let's take an example. So let's say 0, 0, 0, 0, 1, 0, 1, 0. Yes. is how many 0 ones are there? How many 0 1 are there? How many 1 0 are there? 0 1 is 1, 2, 1 0 is 2. And so this would be accept. So in this, if you read 0, right? I will change the state. Keep on writing the 0 here. Keep on reading the zeros. Now when I read 1, right? When I read 1, I go to next state. So I go to next state, and then 0, I come back, and then 1, I go to the already state, and 0, I come back. So I'm not really counting this, right? So just I'm meaning that, okay, 1 0, there is 1 0. Okay. All right. So this is maybe your instant question could be on this, maybe something like, can you write a representation for this? So your answer question. I'm giving a one question for you guys. Okay, so then there was another interesting question. It was sometime 1.6. So this was what was given to us is sigma is AB, and for each k greater than or equal to 1, dk is a dk. So I will ask this. I'm not going to solve this entirely, just giving some hint. What is this language? Can anyone tell? What is this language? It is k minus 1 time you are taking something, some alphabet, and then there is a, right? So in the a is kind of in the kth position, of course. If empty is not there, then it is the kth position, right? At least once. Yeah. And then there is sigma star, which can be like any A, B, C, D, anything. So at least, so this the language is, the language consists of all strings that have at least one A among the last K symbols, right? So among the last K symbols, this is Kth symbol because you have K minus 1 times this. At least the last K symbol is 1. A. So how do you design finite automation for this? So this may, so I can design an NFA simply this sigma, right? Sigma star A, and then this will be something like, right? So this is dot 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 is like there will be some number of symbols, and I'm not going to describe this, but this is something which you can do. Okay, good. So now with this, we will be, so there was one question which I didn't answer, I guess. Let me take that first. There was some question on T. Where was it? Pumping labor. Yes. So there was a question which was Nirbhay has asked. Let's look into his question. What is he saying? Then we will. So his question was around this, sir. If in the previous question, if x implies epsilon, x implies epsilon AB, then we can say if x implies, yes. So what is his question? If you have x implies epsilon also here, then t can imply x tx, and x you can make epsilon, so t can imply t. This is possible. Yes. But this is not the case right here. So okay. So now just to The second state will also be except state. Let's see what is that. Second state will also be except state. Yeah, no, no, but this is NFA, right? So we are writing it, this is NFA. So we have this epsilon, 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 right? So this can be sigma, these are like epsilon transitions are also there, so you don't have to. All right, so before we conclude, so far we have seen in the fire this theory of competition, we have seen how to design a finite automation, and then we have seen regular languages, and we also have seen regular expressions, which are equivalent way of representing regular language. And then we talked about context-free language, which can be represented using context-free grammar, which is also called CFG. And the CFGs can be converted into CNF, which is called Chomsky normal form. We also have seen if you about push down automation, and we said that push down automation is same as non-deterministic push down automation. They are interchangeably used. They are the same concept, but non-deterministic push down automation is not equivalent to deterministic push down automation. They have a non-deterministic one is a slightly more powerful. We also seen last lecture that how do you convert a grammar, right, given a CFG to a PDA. So we have seen all this, and we have done a lot of examples of this. Now, in the next lecture, we will be moving to so next is a more powerful. This machine has infinite amount of memory, right? So the memory will be infinite, unbounded memory, and we will discuss this in the next lecture, that is tomorrow. Tomorrow you will also have a quiz, right? So tomorrow you will have quiz during 2 p.m., which is during the tutorial time. Right? So there will be a quiz and followed by discussion on the quiz. And this is one, and this quiz will be again the syllabus will be okay, so there's slowly, but I can write. I can tell you syllabus is whatever we have done after regular expression. So it will be more like PDA, CFG, CNF, CFG to CNF, and all such thing, and pumping lemma for context-free language. All this. Okay, so this will be the syllabus, and you will have a quiz at 2 p.m. tomorrow. But tomorrow there will be a lecture in the lecture time. So, okay, so with that we will close today. And yeah, so mostly it will be MCQ question. I will decide that by tonight, but mostly it will be MCQ. But most probably you need to solve something, right? Solve something and then answer. Yes. All right. See you.